previous lecture we were discussing about the converging diverging nozzles, and let us work out an illustrative example on that. The problem is as follows: a convergent divergent nozzle is designed to expand air from a chamber in which P0 equal to 800 kPa, which is the stagnation pressure, T0 equal to 40 degree centigrade, to give the Mach number equal to 2.7 at the exit. The area of the throat is 0.08 meter square. This is the given data. So, the following questions are to be answered. Number 1, what is the area of the exit? Number 2, what is the designed mass flow rate? Number 3, what is the lowest back pressure for which there is only subsonic flow throughout the nozzle, only subsonic flow throughout the nozzle. Number 4, what is the design back pressure? Number 5, what is the back pressure for which there is normal shock at the exit plane? Number 6, what is the back pressure for which there is no shock inside the nozzle? Number 7, what is the back pressure range for which there is oblique shock at the exit plane, oblique shock at exit? And number 8, what is the back pressure range for which there is expansion wave at the exit? So, this is the set of questions that we would like to answer. So, let us look into this one by one. First of all, what is the area of the exit? So, to know that, if we refer to A by A star, we know that A by A star is a function of Mach number only. This we had derived earlier. So, based on that we can find out what is AE, because the Mach number at the exit is given, which is 2.7. A star is nothing but area of the throat, because the sonic condition here is reached at the throat. So, from here we can get what is the value of AE, which is 0.255 meter square for this problem. Second part, what is the designed mass flow rate? Remember, the designed mass flow rate corresponds to the star condition, that is m dot design is nothing but rho star A star into U star. Okay. So, individually we have to calculate rho star, A star, U star. So, how do we calculate rho star? Maybe we may calculate T star or P star. So, to calculate T star, let us use any of the isentropic relationships, that is T by T star, or say T0 by T is equal to 1 plus gamma minus 1 by 2 into m square, that we know. So, we can find out what is T star by noting that when the star condition is there, it is m star and m star is equal to 1. So, putting that value, we may find out what is T star. Similarly, we may find out P star, rho star, etc. by using the isentropic equation of change. Now, how do you calculate U star? Remember that U is equal to m into C, which is square root of gamma t. So, U star is equal to m star square root of gamma t star with m star equal to 1. So, if we know t star, we can get U star, and A star is nothing but equal to A throat. So, from all these considerations, by substituting the values, you can calculate what is the m dot design, which for this case will come out to be 146 kg per second. Third part, what is the lowest back pressure for which there is only subsonic flow throughout the nozzle. So, if you look at this pressure diagram for or pressure profile for different back pressures, we can see that the back pressure corresponding to the point C shown in the diagram is the back pressure, lowest back pressure for which there is only subsonic flow throughout the nozzle. So, how do you calculate that one? You know, P by P0 is a function of the Mach number. And you know that you may also write it as A by A star as some another function of Mach number, say F1 Mach number. So, when you know that what is the area of the exit AE by A star, AE we have already evaluated, it is a function of Mach number at the exit. This has two isentropic solutions, one is corresponding to the point C, another is corresponding to the point G shown in the figure. Out of these two, one is the subsonic solution which corresponds to C, another supersonic solution corresponding to G. So, we get the subsonic solution from this, say you can get ME subsonic. Remember that 2.7 is the supersonic solution. So, we can get a subsonic solution also from the A by A star by referring to the isentropic tables. So, once you get that one, you may plug it back here to get P as a function of P0. So, that P will be the lowest back pressure for which the subsonic flow exists throughout the nozzle. So, we can find out this one to be equal to, that is the pressure at this point C, as 780.5 kilopascal. Part 4, what is the design back pressure? The design back pressure you may calculate exactly in the same way as part 3, but you replace the subsonic solution with the supersonic solution. So, here M corresponds to the supersonic solution, that is 2.7, that is pressure, the back pressure, that is pressure at the point G in the figure by P0. So, from that you can get what is the pressure at the point G, which is the design pressure and which may be evaluated as 34.4 kilopascal. Next, let us refer to the part 5. What is the back pressure for which there is normal shock at the exit plane? So, normal shock at the exit plane means we are referring to a condition which is like the back pressure corresponding to E. So, just upstream of the shock it was expanding like an isentropic flow. So, the Mach number was 2.7. What is the Mach number at the downstream of the shock? You get, you know what the relationship between M2 by M1 for the shock. So, from the value of M1 you can get what is the value of M2, which is just at the downstream of the shock. So once you know that what is the value of M2, you also know what is the value of P2 by P1 shock as a function of M2 and M1. So if you know the value of M1 and M2, which you know from the previous step, you can find out the ratio of the pressure downstream and upstream of the shock, and from there you can find out the pressure at E, because you know what is the pressure at G. So P2 by P1 is as good as PE by PG in the figure. So from here you can find out what is PG. So sorry, what is PE. So that value of PE for this problem, the answer will be 286.5 kilopascal. So we know the pressures at points C, E and G, these we have already evaluated, and the remaining 3 parts, the answers to the remaining 3 parts of the problem may be given on the basis of this. Part number 6, what is the back pressure for which there is no shock inside the nozzle. So we can see that the shock occurs outside the nozzle when the back pressure falls below the pressure of the point E. So when P is less than PE, then there is no shock inside the nozzle. Part 7, what is the back pressure range for oblique shock at the exit. So you can see that if the back pressure is between the points E and G marked in the figure, there will be oblique shock inside the nozzle. So the back pressure has to be between PG and PE. And part 8, the back pressure range for expansion wave at the exit when the back pressure falls below the design pressure, that is when P back is less than PG. For example, the point H as shown in the figure, you will get expansion wave at the exit. So depending on the back pressure which is there, you may have different interesting phenomenon at the exit and within the nozzle itself.